In this video, we're going to use the work-energy theorem to solve this problem. So a 300 steel hammerhead of a pile driver is lifted 4 meters above the top of a vertical I-beam, being driven down into the ground. The hammerhead is then dropped, driving the I-beam 8.9 centimeters deeper into the ground. The vertical guide rails exert a constant 65 Newton friction force on the hammerhead. Use the work-energy theorem to find the speed of the hammerhead just as it hits the I-beam and the average force the hammerhead exerts on the I-beam. And we're going to ignore the effects of air resistance. So this problem is one I have come across before. It may seem daunting. However, I like it a lot because it shows how important it is to draw out free body diagrams and uses concepts from previous units. So if you have not already solved it yourself, let's first try to find the speed of the hammerhead right before it hits the I-beam. So in order to solve this problem, there are 3 points of interest. We will call it point 1. This is when the hammerhead is at rest. Point 2 is when the hammerhead contacts the I-beam. And point 3 is when the hammerhead and the I-beam come to a stop. For part A, we will only concern ourselves with point 1 and point 2, since we're only trying to find the speed of the hammerhead just before it hits the I-beam. Since this video is about solving problems using the work-energy theorem, let's solve for the total or net work of the hammerhead. In order to do that, we must first find the net force and displacement of the hammerhead. So let's draw a free body diagram to help us out. This dot is going to represent our hammerhead. We know that the hammerhead is falling due to gravity, so the downward force vector is going to be our weight. Also, according to the problem, we know that the vertical rails are also exerting a constant friction force on the hammerhead. So we're going to have an upward force vector, and we're going to label that our friction force. Now that we've labeled the forces that are acting on the hammerhead, we can write our net force equation, which is the net force is equal to the weight minus the friction. And the reason we don't write it as the friction minus the weight is because the natural direction the hammerhead wants to go is downward. So since the friction is in the opposite direction of this quote-unquote natural movement, we will have the net force is equal to the weight minus the friction. We know that the weight is equal to mass times gravity, so let's substitute that in. So we have the net force is equal to the mass times gravity minus friction. And now we can plug in the information we've been given. So the net force is equal to the mass, which is 300 kilograms, times the gravity, which is 9.8 meters per second squared, minus the friction, which is a constant 65 newtons. And this all simplifies to 2,875 newtons. With the net force, we can solve for the total work done on the hammerhead between point 1 and point 2. If you remember from a couple videos ago, we said that the work is equal to Fd cosine theta. But since we know that the force and displacement vector are in the same direction, which is downward, we know that the cosine theta is going to equal 1. So the work done on the hammerhead equals the net force times the hammerhead's displacement. And now we can plug in the numbers to get that our total work is equal to 2,875 newtons times our displacement, which is 4 meters, which simplifies to 11,500 joules. Finally, we can use the work-energy theorem to solve for the speed of the hammerhead right before it hits the I-beam. So the total work is going to equal the final kinetic energy, which is when the hammerhead makes first contact with the I-beam, which is here, minus the initial kinetic energy, which is when the hammerhead is at rest, which is 0.1. And since we know that the hammerhead is at rest at 0.1, this initial kinetic energy is going to equal 0. So we can simplify this to simply our final kinetic energy, or the kinetic energy at 0.2. And we know that the kinetic energy is equal to 1/2 times the mass times the final velocity squared. And now we can isolate our final velocity variable and solve for the speed of the hammerhead just as it hits the I-beam. So our final velocity is going to equal the square root of 2 times our work total, all divided by the mass. And now all we have to do is plug in the numbers. So our final velocity equals the square root of 2 times our 11,500 joules all divided by the mass of the hammerhead, which is 300 kilograms. And this will equal roughly 8.76 meters per second. Now that we have solved part A, let's do part B. So for part B, we're going to be focusing on point 2, which is where the hammerhead and I-beam first make contact, and point 3, which is where the hammerhead and I-beam come to a halt. Like we did for part A, let's draw a free body diagram. Once again, the dot will represent the hammerhead. And the free body diagram is going to look similar to part A, where we have the weight force vector and we have the friction force vector. The difference now is that we're going to introduce the normal force vector. The reason we're introducing the normal force vector is because this is the force that is being exerted by the I-beam onto the hammerhead. And actually, this is going to be the average force that we're going to be solving for in part B. So now that we've drawn our free body diagram, we can write the net force equation. The net force equation is going to be the net force is equal to the weight minus the friction force minus the normal force. With this net force equation, we can solve for the total work done on the hammerhead during its displacement from point 2 to point 3. The total work done on the hammerhead is going to equal this net force, which is our weight minus the friction force minus the normal force times the displacement from point 2 to point 3. And I'll denote that as 2, 3. Now we can use the work-energy theorem to solve for the normal force. According to the theorem, we can set this equation equal to the final kinetic energy, which is also the kinetic energy at point 3, minus the kinetic energy at point 2, or also known as the initial kinetic energy. So now, let's first isolate the normal force variable and then solve for the normal force. So the normal force is going to equal the weight minus the friction force minus the final kinetic energy, or the kinetic energy at point 3, minus the kinetic energy at point 2, which is the initial kinetic energy, all divided by the displacement from point 2 to point 3. And we can just plug in all the numbers. So the normal force is going to equal the weight, which is 2,940 newtons, minus the friction force, which is 65 newtons, minus the final kinetic energy, which is 0 because the hammerhead and the I-beam are at rest. So we have 0 joules minus the kinetic energy at point 2, which we solved in part A to be 11,500 joules, all divided by the displacement, which was 0.089 meters. The problem gave it in centimeters, but we have to make sure to convert it to meters. And this will all simplify to 132,088.48 newtons.